Alright, so let's talk about the control hazards, which are also called the branch hazard. And these hazards occur when the branch instruction, we cannot determine what instruction to be executed next. So if you recall the in the pipeline structure, when the branch instruction, if it is executed, it must be in the instruction decode phase when the next instruction would be fetched in the instruction phase. Now we do not know whether the instruction that is being fetched is correct or not. It depends on the branch condition. If it satisfies, then we have to fetch the branch instruction. If it does not satisfy, then we can actually fetch the next instruction, which is written in order. So we need to compare registers and compute target early in the pipeline rather than waiting for the branch instruction to reach the execution phase and then decide which instruction to execute. So which means that we need to add additional hardware to do it in the instruction decode stage. So let's assume that we put in the extra hardware so that we can test a register and calculate the branch address and update the PC during the second stage of the pipeline. So in this instruction decode phase. So when the branch instruction is in this instruction decode phase, let's assume that the extra hardware that we add is able to identify whether we need to take the branch or not. So even when the branch instruction in this phase, because it is calculating here, we cannot fetch the next instruction here. So in any case, we need to have a stall in between. Okay, so in this example you can see that we need to have a bubble, at least one bubble for one clock cycle, and then we can fetch the instruction. So in this example, assumes that the conditional branch is taken and the instruction at the destination of the branch is the OR instruction. So you can see that there is a one pipeline stage stall, or bubble in other words. In reality, the process of creating a stall is slightly more complicated. So you can see it here, no matter whether the branch conditions satisfy or not, there is still a bubble in the branch instruction. So in practical, it actually affects the performance a lot, because for example, if you're running a loop and you have to keep calculating the instructions. Again, let's take an example of a loop which we are running 1,000 times. Okay, so if we run the loop 1,000 times, if we keep on checking the instruction, the condition, the branch condition, which means that according to this strategy, we have to keep inserting bubble 1,000 times, which will greatly deteriorate the performance of the processor. Okay, so longer pipelines cannot readily determine branch outcome early and it becomes unstable. The penalty becomes unstable. So we should be coming up with the idea of like predicting the outcome of branch. Like we can assume that the branch is not taken, the branch condition does not satisfy. So in that case, the fetch instruction after the branch, we can execute the program with full speed. So let me go back to the whiteboard. So what I was talking about is this BEQ instruction. Let's say we have x1, x2, and then label, and then we have the add instruction, something, whatever, the OR instruction in order, and then somewhere down below we have this label. Okay, so if we assume that the branch is not taken, then we can execute this next instruction without having the bubble, without having to stall the pipeline clock cycle. In that case, in that assumption, the processor will run at full speed. Only then we have to stall when in the later stage we figured out that this condition satisfy, then we have to actually stall the cycle, stall the currently executed instruction, and convert that into no operation, NOP. Okay, let's see this example here, and you see there is an instruction load word instruction after this BEQ. So if you assume that the branch condition does not satisfy, then it should execute the next instruction, which is LW in here. So it will start executing the next instruction without any delay. Okay, Only then if we figured out that by the time this BAQ instruction reaches to ALU and it figures out that the condition actually satisfied and the instruction being fetched was not supposed to be the next instruction in order, rather the branch instruction, then the processor converts the currently executed instruction into NOP, which is no operation instruction, and fetch the label instruction. Okay, so in that case there will be a bubble of one instruction only. Okay, so in the more realistic branch predictions is such as the static branch prediction, in which we have to assume that some conditional branches as taken and some as untaken. Like we assume that the predict backward branch is taken and predict forward branch is not taken. Let me demonstrate of what do I mean by that. You see, if we have, let's say, some instructions, some set of instructions, let's say add and etc., and then or and whatever, some, let's say another thing, maybe sub, and then we have the instruction BEQ checking x1 or x2 are equal, then jump to loop again. Okay, so loop is somewhere here, and then we have, after this instruction, we have another next instruction in order, let's say LW, something like that. So if we assume that this condition always satisfy, which we have seen in the slide mentioning that the backward branches are always taken. So if we assume that the backward branches, which is going backward, is always taken, and so it will keep going at full speed. So for example, if you're running a loop 1,000 times, then it will keep running 1,000 times without any bubble. Only at the 1,000th iteration, once it start executing this instruction again, it will later figure out in the execution phase, it will figure out that this condition actually satisfied. So the instruction that is being executed is not the correct instruction. Only in that case, it will convert that instruction into NOP, which means that converting into a bubble, and then fetch the actual instruction that is supposed to be fetched. So in this loop of 1,000 iterations, we are inserting only one bubble. So it actually enhances the performance greatly. Alright, so yep. So we have already talked about this. In modern processors, we have the dynamic branch prediction, in which the hardware measures actual branch behavior and it keeps on recording the history of each branch. So it also assumes that the future behavior will continue the trend. If it is wrong, then it will update the history and it will update the condition itself. Okay. So this is about the control hazards, and in summary, pipeline helps us improve the performance by increasing instruction throughput, but it also subject to some hazards, structural hazards, data hazards, and control hazards. And in order to enhance the performance using pipeline, we have to have a more complex hardware design, and that is what we are going to study next in the next few lectures.